So for question 13.35, 36, and 37, they're all kind of related and they're all tied back to this initial data that's presented here. All right, we've got this reaction at time 0, and then at 5 seconds, we're given the reaction again. So there's 0, and then this is 5 seconds. Question 35 asks the half-life, right? Don't even have to do a calculation for question 35, because if we count and look, I've got 12 molecules here at time 0. At time 5 seconds, I've got 6 molecules. So we went from 12 to 6, right? That's a half-life. We've got half of what we started with. So for question 35, right, the half-life is 5 seconds. Didn't have to do a single calculation for that. And then question 36, right? Based on that information, what's the value of the rate constant for that reaction? Well, for question 36, they tell us right above that this is a first order, this half-life follows first order kinetics. So we know, okay, T1/2 equals 0.693 over K. That's the equation for first order half-life. Well, we know half-life is 5 seconds, so we can find K, we can find my rate constant for that reaction. So 5 seconds equals 0.693 over K. I'm going to multiply both sides by K. That cancels out. So I get 5 seconds times K equals 0.693. Divide both sides by 5 seconds, right? This is a first order rate law, so we should have our rate constant have units of inverse seconds, which we do. So 0.693 divided by 5 seconds, I get a half-life, I get a rate constant of 0.1386. Probably we would be good with like 3 significant figures. So probably a rate constant of 0.139 inverse seconds would be a sufficient rate constant for question 36. And then question 37. Question 37 is a good question because it's a challenging question. It's a little bit harder. Right, question 37 basically asks, how many molecules will we have after 8 seconds of this reaction? And so if this was a nice half-life, so if they said after 15 seconds, how many molecules did we have? Well, we could do 5 into 15. That's a nice even half-life. We don't have a nice even half-life because we've got 8 seconds. So it's like a half-life and then part of the next one. So we can kind of guess. We're probably, I would say, going to have like 4 molecules left, probably just guessing on that we've done through one half-life and then we're almost half the next half-life. But how to find that? Well, we know this is a first order reaction. So we know natural log of concentration, right, at time t equals negative kt plus the natural log concentration at time 0. So we use the integrated rate law for a first order reaction to find what's my concentration 8 seconds into this reaction, even though it's a half-life question. So, all right, natural log of concentration time t equals my negative rate constant. So negative 1.39 inverse seconds. And that's 8 seconds into the reaction. Plus my natural log of my initial concentration. Well, initially we had 12 molecules in that flask. And just to make our life easy, we could just say that's a 1 liter flask. So let's just say our initial concentration is 12 molar. All right. So we can go through, we get natural log of concentration, time t equals, so times 8 seconds. So I get a negative 1.1088 plus the natural log of 12. I get 2.48. Add those two together, natural log of concentration at time t equals 1.376. All right, and then so the trick we did in class, right, we're gonna E raised to the natural log concentration at time t, right? E 1.376. So when we take, this gets rid of our natural log, this is gonna give us concentration, then E to 1.36. Right, so our concentration at time t should equal, hopefully it's something around 4. Yeah, so we take E raised to the 1.376 and I get a concentration of about 3.96, right? They asked for the nearest whole number, so yeah, relatively, I'm gonna have about 4 molecules left 8 seconds into this reaction. We will see this. This is why I went over this problem in class or a similar problem in class, because I said like it's chemistry, but I also feel like we're reviewing math as well at the same time. So how to get rid of that natural log, because ultimately we're looking for concentration, right? E raised to the natural log of X gives us X back. So E, the natural log of concentration gives us our concentration. We have to do E to both sides. So E raised to 1.376 gives us that concentration back. If you're ever worried you're doing the wrong thing, well, we have the equation, right, that we use to get it. So I can just plug this concentration. I could plug 3.96 back in here for my initial concentration at time t. Right, I could plug in 3.96 right here and go through this calculation again to make sure everything checked out for that calculation if you weren't confident and or comfortable in those steps.
We never want to have that, right?
Well, we need to get rid of the LN, right? Because we're looking for the question is, what is our concentration, right? This isn't concentration. This isn't concentration. This is natural log of concentration. We want just what is the concentration by itself. So yeah, we want to get rid of that natural log. The LN comes from, right, our integrated rate law for a first order reaction. This is how we can make a linear relationship between concentration and time for a first order reaction by thinking of it as the natural log of concentration over time. So that's where the natural log comes from. So that's how we deal with this rate data, so that we can represent the rate data as a straight line, right? Natural log of concentration over time for a first order reaction gives us a linear relationship, and that's what lets us calculate at any point in time what's my concentration. Even into the future, I can calculate that if I don't have the data for that. Previously, we couldn't do that because when we didn't have the integrated rate law, we were looking at changes in concentration over time, and they weren't linear. So we couldn't exactly say, not having the data in front of us, the data table in front of us, we couldn't calculate at any one point in time exactly what the concentration is, especially into the future for that reaction if we didn't collect that information. So we integrate this data into this format so that we have a linear relationship and we can exactly say what is the concentration at any point for that reaction.